Assalamu alaikum and welcome to lecture number 14, and from this lecture onward we'll start a new chapter, that is transform analysis of linear time invariant system, from the book Discrete Time Signal Processing by Oppenheim. You know, most of your course material is from this book. So from the previous lecture on Z transform, we know that output in Z domain equals to represented by or denoted by y of z, that's equal to h of z and x of z. And you understand h of z is basically called the system function or the transform function, and you know that in time domain output equals to the convolution of the impulse response and x of n are the input signal. So just like in time domain, we say a system, an LTI system, is completely described by the impulse response. You understand the characterization. What do you mean by characterization? That means we can tell about the character of the system. Character means whether the system is stable, unstable, causal, non-causal, right, with memory, without memory, and so on. So all these properties can be, or all these characteristics can be extracted from the impulse response of the system. So similarly, we can say that linear time invariant discrete time system is completely characterized by its system function, that is h of z, knowing the region of convergence. You understand when we do the z transform, when we do the c transform, whether for the signals or for the response of the system, there are two things. One is the algebraic expression or mathematical expression, and the other is the ROC or region of convergence. And you understand two different signals can result into same mathematical expression or algebraic expression in Z domain. Therefore, it is must that we also know the region of convergence. Now, further into the topic, both the frequency response and you also you understand that we can find the frequency response by taking the Fourier transform of the impulse response, right? Taking the Fourier transform of impulse response will result into the frequency response. Similarly, taking the Z transform of the impulse response will result into the system function or the transfer function. So both the frequency response and the system function are extremely useful in analysis and representation of the LTI systems. The frequency response represented by h, e, j, omega of an LTI system as defined as the complex gain that the system applies to the complex exponential signal, the input signal, that's the eigen function, right? So you understand, if we represent a signal in terms of complex exponential signal, then such a signal, when applied to the linear time invariant system, will produce an output signal. And by observing the output signal, we know that basically the input signal, the output signal is scaled version of the input signal, because right, so we say that the input signal, such an input signal means that if the input signal is in terms of complex exponential signal, then such a signal will be called the eigenfunction of the system, and the frequency response will be called as the eigenvalue of the LTI system. So you can also say that in time domain you say, okay, output equals to, output denoted by y of n equals to the impulse response of the system convolved with the input signal. Now taking Fourier transform of both sides, because convolution in time domain results into multiplication in the frequency domain, so that means we can write that y of ej omega, which is output signal in frequency domain, equals to the frequency response of the system times the input signal in the Fourier transform of the input signal. Right, so I hope that's pretty straightforward. Now because you know that the Fourier domain is basically a complex, right? So when something is complex, that means it will have magnitude and as well as the angle or the phase. Okay, so we have two different ways to represent a complex quantity. You understand, we can represent it in polar form, where we have magnitude and the phase, or we have the rectangular form in which we represent a complex number or complex quantity by the real plus the imaginary part of the complex quantity, right? So to find the magnitude, we take a absolute value of the left side, which is y of ej. So y of ej, the absolute of this will be equal to absolute of h of ej omega times the absolute value of the x of ej omega. You understand how we take the absolute value or the magnitude of some complex quantity, right? So if it is in polar form, rectangular form, so absolute quantity is simply the square of real plus square of the imaginary and the square root of the whole, right? The summations absolute values, right? Similarly, to find the angle, right, or the phase, so you understand, or let me write it. Right, so for example, we have two complex numbers, z1 equals to a1 plus jb1 and z2 equals to a2 plus jb2. So to find the magnitude of z1, you understand, we just take the square of the real part plus square of the imaginary part, and then we take the square root of whole. Similarly, right, so like here we have two complex numbers that are multiplied, right, and you understand these complex numbers are not constant, they are the variable, and variable here is omega, so the value of the omega, their value changes, right? So I hope you understand the difference between constant and variable, but just to give you the idea, so I'm just taking the two constant numbers. So similarly, we can find these at absolute for this one. Now for example, we have a third complex number that is equal to, for example, be represented by z, and z equals to z1. Okay, let me call it z3. So z3 will be equal to z1 times z2. Okay, so when we take the magnitude of z3, so magnitude of z3 will be equal to magnitude of right, magnitude of z3 will be equal to magnitude of z1 times the magnitude of z2. Okay, z1 absolute times the z2 absolute. Okay, similarly for the angles, so the angle of z3, let we represent it by z angle, right? You understand this symbol is for the angle, so angle of this will be equal to angle of z1 plus angle of z2, right? So you understand phase angle or angle can be found by, how do you find? We just find it using the tan inverse, right? So Zn angle, for example, Z1 will have angle equal to Z1, and this is equal to uh, um, tangent inverse, right? Imaginary over real. So what is imaginary here? That is B1. So we will just write it B1, or let me change the color. So it will be equal to B1 over a1, right? So in case that the two complex number here like z3 is the equal to product of the two, so that means the overall angle for z3 will be equal to angle of z1 plus angle of z2. Similarly, if we have another complex number, say z4, such that z4 equals to z2 over z3, right? So in this case, you understand the magnitude of z4 will be equal to magnitude of z3 divided z2 divided by sorry, this is z1. Okay, so z2 divided by z1. Similarly, angle of can you tell what will be the angle of z4? So angle of z4 will be equal to angle of z2 minus angle of z1, right? You understand why? Because if they are multiplied, then the corresponding angles will be added, and if they are divided, then the angles will be subtracted. So how to find z2, angle of z2? So that's pretty straightforward. You just say, okay, tan inverse b2 over a2 will be angle of the z, and similarly tan inverse b1 over a1 will be angle of z1, and because they are divided, so the overall angle will be equal to the difference of the two, that is angle of the numerator divided by angle of minus angle of denominator, right? So similarly, if we have, for example, some other number that consists of multiple, for example, we have some z5, such that z5 equals to z1 multiplied by z2, right, multiplied by z3 divided by, for example, z4 and z6, right? So to find the magnitude of z5, it will be equal to magnitude of z1 times magnitude of z2 times the magnitude of z3, and similarly divided by absolute of this and this. Also the angle of z will be equal to, you understand, right, the angle of z5 will be equal to, right, angle of z1 plus angle of z2, right, plus angle of z3 minus angle of z4 and minus angle of z5 6. Okay, so I hope this gives you idea that if you have multiple complex number, then if a complex number equals to product of the two, like here we have this, then the magnitude of y of j omega, it will be equal to product of the magnitudes of the individual numbers. Okay, and similarly angle will be equal to the angle summation of the angles of the two individual quantities, which are h of ej omega and x of ej omega. Now in case they are divided, then the overall angle of the resulting number will be equal to the angle of numerator minus angle of denominator, right? So you understand that the absolute value of this one is called magnitude response, and you understand why we call it magnitude response, right? Because the this is basically response of the system, and which is function of the omega. So this complex number, if we compare with these are the constant numbers, where this one is the variable. So the value of this changes with respect to omega, right? Or we can also call it the gain of the system, right? Similarly, angle of h of j omega is called the phase response, right? Because this is not the constant phase, just like this one. This is, you understand, this is the constant one. Constant one means this stays the same because a and b are, for example, some constant, so it will be constant. Whereas in case of the h of j omega or x of j omega or y of j omega, here they are variables and they are function of the omega, and their values may change, right? Unless they are constant. For example, y of j equals to, for example, 2, 3 or 5 or whatever, then in that case it's constant. But otherwise in general they are variable and they're function of the omega, and there's some term involved where the omega where the value changes with respect to the omega. So the angle is called the phase response, because right, or the phase shift of the system. So after defining and understanding what is magnitude and what is phase, so the magnitude and phase effects which we have done in the previous slides can be either desirable, that we want them to be so, or they can be undesirable as well. So in case they are undesirable, then we call them the magnitude and phase distortions. Okay, so for the case of magnitude, we say this is magnitude distortion, and for the case of phase, we say this is the phase distortion. So let's consider an ideal delay system. You understand what is an ideal delay system? Ideal delay system is a system that will delay the input signal by some specified amount. So because we are in discrete domain, so it can delay it by a factor of 1, 2, 3 and so on, right? So in general we represent delay by nd. So whatever you give it input, the output is delayed version of that input, and the amount of delay is equal to nd. So when you find the impulse response of the system, the impulse response, you understand, is the output of the system when the input is impulse. So we replace x by impulse, so the output is replaced by h. So I for ideal and d for delayed, so HID equals to this one. And when we take the Fourier transform of this one, right, so you understand how we will take Fourier transform, right? You just sum it from minus infinity up to infinity, and you say, okay, x of n times e power minus j omega n. So hope you can easily find it. For the impulse, we get the Fourier transform equals to 1, whereas this is the delayed impulse, so 1 multiplied by amount of delay. If you replace delay by 0, so 1 multiplied by this will result into 1. Anyway, so the magnitude of this one will be equal to 1, you understand, right? So a complex exponential has because magnitude equal to 1, and this is the angle, which is omega nd. So the phase is basically minus omega nd, right? And we assume that the omega, this is valid for omega is less than pi. So this is how we represent the phase. Okay, this is how we find the phase. Hopefully you know already how to find the phase and magnitude, but this is the phase response for the ideal delay system, and you understand this is also a function of omega. It's not a constant phase, in contrary to the complex number in general, right? Fixed complex number, because this complex number is variable and this is function of omega. So as omega increases, this will increase. Then the term comes group delay. Group delay basically is a measure of linearity of the phase, that how linear is the phase. And to find the linearity of the phase, we normally, you understand, we take the derivative. If we take the derivative, then we can tell whether something is linear or how linear it is. Okay, so the angle, you understand, of the response is basically equal to omega phi naught minus the omega nd, right? So that's what you get from the system. Okay, so if I take derivative of this angle, then I get I mean we can find it minus d over dw with, you understand, because we are in the frequency domain, the independent variable is frequency, so we take the derivative of this with respect to the omega. So you understand, when we take derivative, if something is linear, then we get a constant value, right? So for example, if a signal is, or some variable is, for example, that's your omega, and this is something like this. So whether it's right, whether it's equal to for example, I just say angle of h of j omega, right? So if this is equal to, for example, uh, alpha times omega, then we get a constant value, right? So again, by definition, you understand the group delay is basically measure of linearity of the phase. So for like this particular case, this is constant, right? This is a ramp. So taking derivative of this will result into a. So whether a is 1 or 1 by 2 or 2 or whatever, but we get a constant, right? So if we get a constant, that means the group delay measure of linearity will be constant. So deviation of the group delay from constant indicates the degree of non-linearity of the phase. So I hope that's quite straightforward. You might have noticed that phase angle of any complex number is not uniquely defined, since any integer multiple of 2 pi can be added without affecting the complex number. And the phase angle we normally compute is using the tangent inverse of, you understand, imaginary or the real. So the value given by this is called as the principal value, and we denote the principal value of the phase as capital, you understand, ARG, that is argument of HEJ omega. And this principal value uh, has value between minus pi to pi. So any other angle that gives the correct complex value can be represented in terms of the principal value as the argument or angle of h of ej omega equals to the principal value plus 2 pi r omega. You understand, r is function of omega, and r omega can be positive or negative integer that can be different at each value of omega. You understand, because we have written omega here, so that is, it is function of the omega. In many cases, the principal value will exhibit discontinuities of 2 pi radians when viewed as a function of omega. It is shown here in the figure. So if you look at carefully in the figure part A, you can spot that the phase function plotted exceeds the minus pi to plus pi values. You understand, you see it can be extended roughly more than minus 3 pi or so. The values shown in figure B are the principal values, and it can be observed that the principal values has jump of 2 pi owing to the integer multiples of 2 pi that must be subtracted in certain regions to bring the phase curve within the range of the principal value. Similarly, figure C shows the corresponding value of r omega as we discussed in the previous slide. Thus, adding this will result into the continuous values of the phase. In general, we can think of broadband signal as superposition of the narrowband signals, and each narrowband signal has different center frequency. So if the group delay as defined in the previous slides, so the constant group delay means that each frequency component in the narrow band will go under identical delay. But if the group delay is not constant, then there will be different delays applied to different frequency packets. So it will result into, if the group delay is different, then it will result into dispersion in time of the output signal energy, right? So that's why we want the group delay to be constant. So we can say that non-linearity of phase or equivalently non-constant group delay results in time dispersion. To understand the concepts of group delay, let's consider an example. Suppose we have a system that has a system function equal to as defined here, which so this consists of two parts, right? The product of the two system, that is h1 of z is this one and h2 of z is this one, and we have k running from minus 1 up to 4, and we have the values of ck equals to this for k equals to 1 to 4. Shown in the top figure is the phase response, that is principal phase response is shown here, whereas unwrapped or the continuous response is shown here. So we have, if you look at the principal phase response, we can see that there are multiple discontinuities you can observe, and these discontinuities has size equal to 2 pi. That's from here to here it is 2 pi. Okay. Whereas in the figure below we have the continuous phase response. Here we have removed the jumps of the size 2 pi. You understand, when we take the, in case of principal value, we take just the tangent inverse, and you understand there we have maximum frequency in the range of minus pi to pi, or we can say the maximum frequency is 2 pi. Shown on this slide are two graphs. The upper one is basically group delay of the system. We have presented in the previous slide, and the bottom figure shows the magnitude of the frequency response or the magnitude response. So here we have interesting observation, because so we can see the unwrapped, right? This is the unwrapped phase response, and we can observe that it's monotonically decreasing everywhere except with omega equals to plus minus 0.8 pi, right? So you can see there is a decrease here, and again we have a decrease here. So we have positive group delay everywhere except these 2 points. We have peaks in these region. This one has frequency of 0. So it peaks, the continuous phase has the maximum negative slopes. Here and here. Where at these dips, the phase has the positive slopes. Whereas in case of the magnitude response, we have maximum values around plus minus 0.4 pi. Shown in the slide is on the top is the signal x of n that consists of three narrowband pulses separated in time. That is, one is from 0 to almost 50, the other one is from somehow maybe 75 up to 125, and the third one is from 125 up to something like 175 or so. And the bottom figure shows the corresponding magnitude of the input signal. The three input signals has frequencies respectively omega 1 equals to 0.2 pi, omega 2 equals to 0.4 pi, and omega 3 equals to 0.8 pi. So shown in the bottom is the Fourier transform, that is the magnitude response of the x of n, and we can see that significant energies centered and concentrated around 0.8, right, plus minus 0.8, plus minus 0.4, and plus minus 0.2 pi. Each frequency pulse contributes in frequency domain a band of frequencies centered at the center of the sinusoid. Like we have at 0.8 centered, we have a band of frequency, again at 0.4, at 0.2, similarly in the positive values of omega also. So if we input this signal with the transfer function as defined previously, each of the frequency packets or groups associated with each of the narrowband pulses will be affected by the filter response magnitude and the group delay. From the filter center frequencies, from the filter frequency response, we see that the frequency group centered and concentrated around 0.2 pi, that is centered around 0.2 pi. Let me this one, okay. So this one will have slight amplitude gain, whereas those at around 0.4 pi, if you can see that it has higher amplitude here, right? So 0.4 pi frequencies, right? So I hope that's clear to you that we have a signal that consists of three components, that right? So each component, the first component has frequency around 0.2 pi, the second one around 0.4 pi, and the third one around 0.8 pi. So we have original signal that composed of these, and when we take the Fourier transform of that signal, so we get this magnitude spectrum for that discrete time signal, and this is the magnitude response of the system we have discussed, right? So if we look at carefully, so you can see that because at the frequency around 0.4 pi, the magnitude response is around 2. So that means those frequency components that are around 0.4, whether plus or minus, right? So I think that's visible to you. Whether they are plus or minus, they will be get an amplification of around 2. Now coming to the third frequency component present in the input signal, that is 0.8, right? So plus minus 0.8, that means 0.8 pi here, and we also talk about the 0.8 pi here. So if we look at the corresponding values of the response, right? So the response has very small value, right? For both, you understand that it's in group 0. Plus minus 0.8 pi, right? So in that case, because the response has very small value, whether it's plus or minus, then that means that part will be eliminated, right? So that means the input signal having the highest frequency component, which is 0.8 pi, that will be eliminated from the signal. Thus the output signal will contain the values that are for the two frequency component, that is 0.2 pi and 0.4 pi. So the component value that is around 0.2 pi frequency, that will be amplified but to with a value of almost, if you look at this one, so for 0.2 pi it's almost 1 or slightly greater than 1, but for the case of 0.4 pi it will be amplified 2 times, right? So it will have gain equal to twice. So whatever the amplitude at the input was, now it will have twice of that. But as far as the frequency component present at 0.8 pi will have output almost equal to 0. And you understand why? Because the response has very small value for this frequency. So we say the highest frequency component is significantly attenuated. Similarly, coming to the second part, that is group delay. So you can observe that the group delay around plus minus 0.2 pi is the maximum, that's around 150, right? So that means the frequency components that are around 0.2 pi plus minus 0.2 pi, they will be delayed by large amount in comparison with the 0.4 pi, which suffers from very small or negligible delay. So that's why you can see that in the output signal we find that the frequency component, the signal containing frequency component of around plus minus 0 to pi, they are delayed, right? So like they are inverted, right? That means in the original signal, if you can observe, I'll just give you as a homework, maybe you observe where is the spot, right? I just give the plot here for the signal containing 3 different frequencies, and you just tell me which signal or which part has the highest frequency and which one has the lowest part. But anyway, if you compare with the original, so you hopefully you can spot that the signal this was the in time domain, it was after this signal, but after passing through the system, now because the signal having frequency of 0. plus minus 0.2 pi will suffer more from the delay, right? So it will suffer more delay, and the signal that is around 0.4 pi will suffer very small delay. So that's why they are, I think, inverted. But I'll give you as a homework, and you just tell me whether it's so, whether I'm right or this is not so. So that's all for today's lecture, and see you in the live session. There will have, hopefully you will go through it before the lecture so that we can have discussion and question answer session there. So that's all for today. Allah Hafiz.